We are from VelTech University, and we are presenting the structure and analysis of the frame of an amphibian vehicle. This is our final project. The internal guide is Dr. R. Velu. Basically, in this project, we have dealt with the structural analysis and optimization of an amphibian vehicle. As we see in this abstract, what we are going to do is we are going to take a UAV and then optimize its structure. By optimizing, what we mean is we are going to reduce its packing size and leave its performance undisturbed. Reduction in mass of structure will enable the quadcopter to carry more payload, and it will also reduce its fabrication cost and operation. This will enable us to carry more payload. The amphibian quadcopter, what does it mean? Basically, it is quadcopter is a multi-rotor or rotorcraft which works on rotor-based propulsion. An amphibian quadcopter would mean that something that is able to travel in more than one mode of transportation. That it could be land and air, water and land, air and land, or sometimes the three-mode transportation. In this, we are going to, as said, we are going to structurally design and analyze the amphibian vehicle. The literature survey over here, we have read some literatures to design the amphibian vehicle. The first of which is the NASA Ames Research Center's literature. They have developed one of the first UAVs which could carry about 3.5 kg. It is made out of balsa wood. In this, they majorly covered problems that was in water sources landing and water sources takeoff. This helped us in also designing our amphibian vehicle. So the next one is Malaysian University. What they did is they have designed and analyzed the three-mode amphibian vehicle. As spoken before, it has VTOL capabilities, that is vertical land off and taking. Whatever design parameters and considerations were done in this paper, we have taken those, because it is very important that our vehicle also moves in the three-mode. Also, the autonomous amphibian vehicle AAV designed by Frederick and Knockleby. This is the first amphibian vehicle to use ABS. As you would see in the later parts of this report, ABS is one of the most important materials that we use in our analysis. This ABS will be considered from now onwards, because it has many unique properties and it is very useful in vehicles such as these. What is our problem definition? We were given such a diagram and told to reduce its packing size by 40% and reduce its mass by 30%. We expect our frame to have a reduced weight of 40%, and also we expect to achieve our objective of 7 kilogram payload capability. We would be doing this by systematically analyzing and optimizing our model. The proposed methodology is that we will first collect the literature surveys and design specifications. Then we would make some conceptual sketches and primary design. Then we would calculate the design theoretically, analyze it, and then optimize it. These two last stages would be done completely using software. This solution means that we are going to deal with the dimensions. We reduce the packing size in CATIA V5 without affecting any features. We use a scaling tool to do the packing size reduction. In the next slide, we will see that we have structurally analyzed it to make sure there is no drop in performance. This is the scale model. We can see the dimensions over here, 360 by 180 by 108. This reduces the weight, we analyzed the structure as said before using ANSYS. The specifications for that, we used aluminum alloy with which showed a mass of 1.2 kg and a volume of 0.42 kg. There was a load applied of 4 kilogram on the ends of the arm, and the base is fixed for the analysis. That means zero displacement. The arm means that this arm that's depicted on the diagram. Let's move on. The mesh was carried out we did an automatic mesh. The results are shown in the diagram. Basically, the mesh was a tetrahedron type mesh with 5381 nodes and 2218 elements. So moving on, the results, we analyzed for von Mises stress and deformation. Von Mises stress shown here is 15.413 megapascal. Compared to aluminium, it is very less, hence the design is safe. And also the deformation value shown over here would be 0.7932, which is less according to the SAE loading code, which for aluminium is 1.25 mm. Since these two are less, we can assume that the design is safe. But to reduce more vibrations and also to make the design better, to carry more payload, what we did is we made small design iterations. We shown here is model number 2. We changed the circular cross section to a hollow square. Also, we made the cross link equidistant from the base. The square arm ensured that the structure became more strong because it reduced the bending stress due to its low section modulus. We can see here itself that the equidistant arms and the square arms in the diagram. Model number 3 has a simple change that ribs replaced our equidistant arms, and this would help a lot in the strength as seen in the analysis results. Yeah, in the primary results we got 3 analysis, and we see the rib model as the best. We finalize the rib model as amphibious vehicle model because in the results the stress sustained and the deformation is comparatively lower for this model than the others. Also, these are the materials that we have used for analysis. Aluminum alloy, ABS, we have used aluminum alloy AA5052H32, and we have used composite materials and carbon fibers. These are the analysis. In this we can see that the least mass is for model number 2, but model number 3 also comes close by if we round off model number 2. As I said before, model number 3 is very important from now onwards, because it would have competitive values in all these analysis that we are going to see. First was mass, next is deformation. We can see there's 1.60. Even though ABS has one of the highest deformation values, most of it lies very less, or it is comparatively lower than the SA loading code that we had seen before. So here too we can see there's 1.63 for model number 3 ABS. This would be from here on we would see what is the stress. The stress is just 5.7 megapascal for model number 3, which is very less compared to others. So we chose ABS because of that. It can reduce the mass by 50%. Deformation values were low. The stress sustained by the object was 80% less than the maximum stress value. It costed less in comparison with the other materials also, which is a very important factor in our analysis. Later on we optimize the structure using the shape optimization tool to further reduce the weight and remove any unwanted links. The constraints as said were similar to the structural analysis. We have the material as ABS, we have the fixed base, and the loads, 4 kilo loads were applied on each end of the arms. Later we ran the tool checking for von Mises stress and deformation. What happened after that is that it showed us reduction in weight and unwanted links in the model number 3. These links will be further removed and showed in the final model. The results of this optimization to a 23% reduction in the mass. This also showed us the red dots in this image show the unwanted links in our design. So finally, we have reduced the mass by a further 23% compared to the previous 25% that we had reduced due to material changes and small design changes. So we have successfully completed the structure analysis and optimization. Given model was slightly modified due to its vibration and stress reduced by 45%. The first phase we modified the model and got 25%, and then we optimized the model and got 23% reduction. After analysis, we chose ABS as material due to various conditions. Also, the model's mass had reduced by 48%, and the material can carry and the model can carry a payload of 7 kilogram, which is a very important objective for us. 7 kilogram payload. Moving on, this even though our project is a success, we could emphasize on the future work. We could design a model with higher payload, and the current material choices could be better. Material choices could be better, and also material choices could be better. The structural designs could have non-geometrical shapes that aid in the mass reduction and stability of the body. This could help in improvement of endurance and range, which will obviously help us in improving our quadcopter further. Yes, moving on. The references for our project is shown here, and also finally, thank you.